This video is about the divergence theorem, which is the 3D analog of the normal form of Green's theorem. In this video, we will briefly review the normal form of Green's theorem and what it means, and then we will talk about the divergence theorem and how we extend this idea to 3D instead of 2D. And then we'll have time for at least one example and maybe two examples applying divergence theorem to evaluate an integral. Okay, so this is the normal form of Green's theorem. And it says, provided all of this is true. So if R is a simply connected region, that means every simple closed curve that lies in R contains only points that are in R. If that's true, and R has a piecewise smooth boundary C, so that's this boundary here, and it's oriented counterclockwise, and it's traversed exactly once. And our field is a field in the plane, and its component functions m and n have continuous first partial derivatives in an open region containing R. So I put a little dotted line here, so that just means that these two functions are continuous inside that little dotted line and in the region R itself and on the boundary of RC. So those component functions are continuous there, and their derivatives are first partial derivatives, are continuous. If all of that is true, then this line integral over C of f dotted with the outward unit normal vector is equal to the double integral over R of the divergence of f. So let's talk about what this means. Let's talk about what the left-hand side means, and let's talk about what the right-hand side means. Now, I've labeled this the flux across C. Now, the interpretation of this depends entirely on what f represents. So let's just say, so that we have like a physical interpretation of this, that f represents the velocity of some fluid. So this gives me the velocity at any point in the fluid. Well, if I take the dot product of that fluid velocity with n hat, basically what that's doing is it's finding the component of the velocity that is crossing that curve, component of the velocity that's parallel to n hat. So let's just think about this a little bit more. So I'm going around this curve, and at every point on the curve, I've got a fluid velocity there. Now, at each point, I want to take the dot product of f with n hat, and n hat is the outward unit normal. So let's say we're on just a little part of the curve like this, and it looks like this. So this is C. If I'm at this location, the unit tangent vector goes that way. The unit normal vector that we're accustomed to points in the direction we're turning. So that's our old unit normal vector. But when we're thinking about flux, we're not thinking about the unit normal vector in this direction. We're always thinking about the outward unit normal. So that's the other one. That's the one that's going out from our curve like this. If this f here is the fluid velocity at this location, f dot n is the component of the fluid velocity that is parallel to n hat. So if the fluid is tending to cross that curve, that dot product is going to be positive. If the fluid is tending to cross that curve by going into the region as opposed to going out of the region, that dot product would be negative. But we calculate the dot product. It's just a scalar. We take that scalar, which is positive when the fluid is going out of the region, and it's negative when the fluid is going into the region, and we multiply it by a tiny length along the curve, and then we add all of those together, and we call that the flux. When we're done, when we add all those together, we're going to get a scalar here. If that scalar is positive, that means more fluid is going out than is coming into that region. If that scalar is negative, that means more fluid is going into the region than is going out of that region. And that's what that left-hand side of that equation represents. It's sort of that net version of the or that net amount of fluid going in versus fluid going out. We're saying how much, it's a measure of how much is going in versus out. Okay, that's flux across C. And we're counting it as positive when it goes out. Well, the normal form of Green's theorem says, instead of doing that, instead of doing the line integral over C and looking at the normal component of your velocity vector and then adding all of those up and multiplying by a tiny length, instead of doing that, don't do that. They said, do this instead. Instead of doing that, you can evaluate the double integral over R of the divergence multiplied by a tiny area piece. So what this side says is, okay, go take your region R and split it into a bunch of little rectangles. Maybe the area of each of those rectangles is delta X times delta Y, which we can put together to call delta A. And then at each little rectangle in the region, you want to look at the flux, or not, excuse me, the flux, the divergence in that rectangle. Now remember what we said, what divergence represented. We said informally, divergence represents how much that fluid is spreading out from that point. If the divergence is positive, that means the fluid is diverging from that point, sort of spreading out. If the divergence is negative, that means the fluid is sort of coming together at that location. But here's the idea. We're saying the flux across C, like that's the amount of fluid that's going out of that boundary on the outside for C. That's the same, I can find that flux across C by doing this instead. So what I'll do is I'll calculate the divergence, that's our measure of how much the fluid is diverging at a certain location, and I'll multiply it by dA, and then I'll add all of those together. And I think this makes a lot of sense because whatever is going out of this little rectangle is going into that one, and whatever is going out of this one is going into that one. So all of those are going to cancel, except for the ones on the very edge. The ones on the very edge are actually going to count toward our flux. Now in practice, this tends to be easier to evaluate than this. So rather than evaluating this line integral, we evaluate this double integral over R instead. So this is a very nice theorem, and it allows us to find flux over a closed curve C. So I guess we could put a little circle there. So our curve is closed by evaluating the double integral of the divergence instead. So now, because of this, we can come up with a slightly more formal definition of divergence. We were saying before that it's a measure of how much that fluid is spreading out at a point, or how much the field is diverging from a point. Now we can see that in this context, when we're in the plane, we have a field with components m and n. This divergence is giving us flux per unit area. So we've got flux per unit area in each piece. We multiply by area, and then we add them together, and we get the total flux. Okay, so that's what that says. The divergence theorem and Gauss's theorem, or Gauss's theorem, Gauss's divergence theorem, those are all the same thing. That is exactly like this. Not exactly, it's almost exactly like this, just in 3D instead of in 2D. So here's the divergence theorem. It says, let Q be a solid region bounded by a closed surface, S, oriented by an outward unit normal. So I've got S over here. Maybe the bottom surface is given by S2, the top surface is given by S1, and S is the boundary. It's the union of S1 with S2. Q is the solid region inside, and these are oriented by outward unit normals. So the normal vector on S1 and the normal vector on S2, they point out. They don't point into Q, they point out of Q. Then if F is a field with components m, n, and p, and m, n, and p have continuous first partial derivatives in Q, then this surface integral is equal to the double integral of the divergence of F. Or I think I said that wrong. this surface integral is equal to the triple integral of the divergence of f. And let's think about what this represents. This is still flux. But remember what flux represents in this context. This is the component of the velocity that's going out, the component of the velocity that's parallel to that outward unit normal. And then we multiply by a little area piece. So this is flux across the surface S. But flux across the surface S, if F represents the velocity of a fluid, is a volumetric flow rate. This is the volume of fluid moving through the surface per unit time. And if you're wondering, like, where's the time coming from? I don't see any time. It's in that velocity vector right there. Okay, so this says the flux of S, or of the flux of, excuse me, I'm so sorry. The flux across the surface S, which is the volume of fluid moving through the surface S per unit time, is equal to the triple integral of divergence over the region Q. So over here, we said after we understood this equality, we could come up with this better interpretation of divergence. We said, well, if this is divergence times area that gives me flux, divergence must be flux per unit area if we have a field in the plane. Now we see if we have a field in three-dimensional space, this must be flux per unit volume. So we take flux per unit volume and we multiply by volume, and then we add all of that together and we get flux. And you say, well, what's flux? Well, it's volume moving, volume of fluid moving through the surface per unit time. So now we have this new interpretation of the divergence. Now over here, we're thinking of divergence as flux in a little tiny rectangle with area delta x times delta y. Divergence. Now we're thinking of that as, so that's delta y, isn't it? Thinking of that as flux through a tiny cube. And what goes into this cube probably goes out of that cube as well. But if it goes out of that cube, well, then it goes into the adjacent cube. And then whatever goes into that one comes out of that one, and so on. We get a bunch of little cubes lined up like this. And really, only the flux on that boundary ends up counting, because what is positive for this cube is negative for the next one until we get some over here. So this makes sense, I think, when we think about what divergence means. When we remember that it's that tendency of the field to spread out at a point. Now we're saying more precisely, it's that flux per unit volume. Okay, so if I want to use this, all I need to do is check these conditions. So make sure you have a solid region Q, and we've got a closed surface S. We want to remember that we are thinking of that normal as outward oriented. If it's inward oriented, we'll have to multiply it by -1 in order for these to be equal to each other. Then the flux through the surface can be evaluated by doing this instead. And this is actually quite nice. Like, this is a pretty simple integral to evaluate for something like this. I just let z go from the equation of this surface to the equation of this surface, I look at the projection onto the XY plane. I describe that as my region R. And then we just evaluate this one triple integral. Now over here, I would need my field. In terms of X, Y, and Z, I would need n hat. In terms of, or excuse me, I initially have my field in terms of X, Y, and Z. But now I need my field in terms of X and Y. I need n hat in terms of X and Y for this surface. And then I need to project that surface onto the XY plane and evaluate a double integral. And then I would have to do the same thing for the other surface, add those together and get some result. It's much, much simpler to just find the divergence of the field and take its triple integral over Q. So this is a very nice theorem. Gauss came up with it. He's kind of a big deal. Let's see. Let's actually apply that. Okay. So here's a question that says, use the divergence theorem to evaluate the flux integral, the flux surface integral of this field where S is a surface bounded by the planes y equals 4, z equals 4 minus x, and the coordinate planes. So let's see, what do we have here? The first thing I will do, the first thing I would recommend that anyone do is sketch the surface S, and then of course the solid region Q inside. So S is that surface on the boundary, and you want to remember that Q is that solid region inside the surface. When X equals 0, Z equals 4. When X equals 4, Z equals 0. So in the XZ plane, what we see is just a line here. And then when Y equals 4, we're actually going to see the same line. Okay. I think that's it. Here's Y equals 4. Here's Z equals 4 minus X. Then we've got a boundary given by the YZ plane in the back, the XZ plane on the side, and the XY plane on the bottom. Those are the 3 coordinate planes. So that's our solid region. Not too bad. Now, if I were to do this surface integral, it'd actually be kind of a pain, because how many surfaces do we have here? We'd have this top surface, the one in the YZ plane, the one in the XZ plane, and the one in the XY plane, and then this one over here parallel to the XZ plane at Y equals 4. So I'd have 1, 2, 3, 4, and then this surface on top, that plane. Then there'd be 5 different surface integrals that you would have to evaluate. But the normal vectors for most of those were pretty simple, so it wouldn't be that difficult, but gosh, it would be tedious. We'd have to do 5 surface integrals. Now, rather than doing 5 surface integrals, we can use the divergence theorem and just compute the triple integral of the divergence of this field over Q instead. Okay, and where Q is the region inside. So I'll just label that. Q is the interior of this region. And the surface S is on the outside. Okay. Now let's check the conditions of the divergence theorem. Okay, so let's got my theorem back here. Q is a solid region bounded by a closed surface. It sure is. S is oriented by an outward unit normal. Well, I haven't oriented it, but we could orient it. There would be a normal vector sort of pointing out at us like this. Actually, probably be pointing up, not down. So that's a normal. Then we'd have a normal over here. It should actually be pointing parallel to the y-axis. Then we'd have a normal vector over here. And then there's this normal here is supposed to be in this plane z equals 4 minus x. In the back of this piece, in the yz plane, we'd have a normal that's going parallel to the x-axis. So that's n hat there. And then on the bottom, we might have a normal vector that's pointing straight down. So yes, we can imagine that this is a surface and all of those normal vectors are pointing out rather than pointing in. Just keep that in mind when we interpret our answer. Okay, so we've got a solid region Q with a closed surface S bounded by outward or oriented with outward unit normals. That's totally fine. And now what do we need? We need our field to have components that have continuous first partial derivatives in that region Q. And the field is very simple. We just have polynomials, very simple polynomials in x, y, and z. So those three conditions are satisfied. So let's write those down. We have a solid region Q. We've got a closed surface S is the boundary of Q. Oriented outward. And F is a field with polynomials for its component functions, excuse me. F has these components and they have continuous first partial derivatives everywhere, so they certainly have continuous first partial derivatives in Q. And I'll just say because they are polynomials. In X, Y, and Z. All right, so divergence theorem may be applied here. So now we'll just state the divergence theorem. And then we'll set up and evaluate that triple integral. And remember all the work that you're getting to avoid here. We would have to do 5 different surface integrals for this and then add them together. But instead of doing that, we're saying you don't have to do these 5 surface integrals. Instead, do this, the triple integral over Q of the divergence of F. So we need the divergence of F, and then we need to describe Q. So the divergence of F, we can think of that as the dot product with the del operator. So here's my operator. I'm dotting that with x, y, z, and x plus y. Well, this is going to be really simple. I've got a constant times x here as far as x is concerned. The derivative of a constant times x is just our constant. There are no y's in this, so that's 0 and that's 0. There are no z's in that. So we have y plus 0, which is 0. So we just integrate y. That's going to be super simple. Now we just have to describe q. The region in the xy plane is this region down here. So that's our region R. And we need z to go from a function to a function. And then we need to describe that region R. So z starts in the xy plane. And that's given by z equals 0. So that's just the bottom function. And we want z to go from the bottom function to the top function. And the top function in this case is just 4 minus x. And then we say, okay, those are going to be our bounds for z. And to find our bounds for x and y, we look at the projection onto the xy plane. It looks like a little rectangle. Actually, it's a square. X goes from 0 to 4, y goes from 0 to 4. Nice, easy bounds for both variables. Okay, so we've got these bounds for x and y. We need to integrate with respect to z before we integrate with respect to x. And now we will set up our triple integral. And then, of course, we can interpret what we get. So we have the double integral over the surface of this triple integral over Q of the divergence of F. The divergence just happens to be y, and we'll integrate with respect to z first, and then x, and then y. X and y both go from 0 to 4, and we said that z goes from 0, that's in the xy plane, to this top function, z equals 4 minus x. And then we just work our way out. Start on the inside and evaluate integrals. Y is constant with respect to z. The antiderivative of a constant with respect to z is that constant times z. Then you evaluate at z equals 0 and z equals 4 minus x, and then you subtract. Okay, and z equals 0, we just get 0, so I didn't write it down. Now we anti-differentiate with respect to y. 4 minus x is constant with respect to y, so you can bring that down. Antiderivative of y with respect to y. Add 1 to the exponent, divide by the new exponent. Substitute in y equals 0 and y equals 4 and subtract by the fundamental theorem. So I'm pulling out that constant. Evaluate y squared at 4, we get 16. Evaluate y squared at 0, we get 0. So I have that right there. And so I have 16 times 2 is 8. The integral from 0 to 4 of 4 minus x with respect to x. Easy integration. Add 1 to the exponent, divide by the new exponent. Evaluate this from 0 to 4. So you have 16 minus 1/2 of 16. And then when we evaluate that at 0, we get 0. So we've got 16 minus 8, which is 8, and 8 times 8 is 64. Say 64 what? Well, it depends on the units of F and ds, but if F was in meters per second, so this is velocity of some fluid, and if S is measured in square meters, because this is surface area, we'd have meters cubed per second. So this is 64 cubic units of volume per unit time. And I'm not really sure what our dimensions are. But if F represents the velocity of some fluid, that is the flux. Now the fact that that is 64, what does that mean? It doesn't mean that no fluid is going into the solid region Q, but it means that net, after all the fluid that was coming into Q was counted, and after all the fluid that was going out of Q was counted, the net flux of that fluid is, well, it's going out more than it's coming in, and it's coming out at 64 units cubed per unit time net. So that's the divergence theorem. Let's do one more example. Okay, it says use the divergence theorem to evaluate this surface integral. And we've got our field F, and Q is a solid region bounded by this, and S is its boundary. So let's sketch it first. Always start by sketching. So we're sketching the solid region Q and its boundary S. Now, it's not 100% obvious what that surface is, but I notice I can get rid of that square root by squaring both sides. Oops, that should be minus y squared. Now, because this was a positive square root, it was implied that z was greater than or equal to 0. So we've got this, and then if we add x squared and y squared to both sides, we get this. So we say, hey, guess what? That is a sphere of radius 4, centered at the origin, but it's only the top half. It's just that top half of the sphere. And it's just the surface. That's what that represents. So x goes from -4 to 4, y goes from -4 to 4. Z would go from -4 to 4, but we're only talking about the top half. So Z goes from 0 to 4. So this crosses at 4 there. So that is the top part of S. So I could call this S1. And Z equals 0 is the bottom half. So Z equals 0 is down here. That's S2. And S is the union of S1 and S2. And we see it's a solid region, or yes, it's a boundary of a solid region. It's a closed surface. I've got this part, and then we sort of put a bottom on it with that Z equals 0. So Q is the region inside. Okay. Now let's check the conditions of our theorem. I was about to write Green's theorem. Say the divergence theorem or Gauss's theorem, same thing, or Gauss's divergence theorem. Do we have a solid region Q? We do. The closed boundary S, yes. And then we're supposed to make sure it's oriented outward. So we would put a normal vector, let's say here. We want to make that our orientation. And on the bottom, that normal vector is going to point straight down because it's pointing outward from Q. What else do we need? Well, we need the field to have components that have continuous first partial derivatives in Q. The components of the field are polynomials, so we have no problem with that. So Mn and P are polynomials in X, Y, and Z. So they have continuous first partials throughout the entire, all of three-dimensional space. So they certainly have continuous first partials in Q, first partial derivatives. Okay, so the conditions hold. Now all we have to do is write down the divergence theorem. The divergence theorem says, instead of evaluating that surface integral over S1 and the surface integral over S2, which requires finding this field in terms of X, Y, and Z as a function of X and Y on S1, finding the normal vector to S1, taking a dot product, and then integrating over the projection of S1 onto the XY plane, and then doing the same thing for S2, and then integrating. Instead of doing both of those surface integrals, we can do this single triple integral instead. And this is still going to give us the flux through the surface S. So we just need to find the divergence of F and then evaluate the triple integral over Q. Or yes, we're going to evaluate the triple integral over Q of the divergence of F. So we need the divergence, and then we need a description for Q so that we can integrate there. And since Q is part of a sphere centered at the origin, it's probably best to go to spherical coordinates, provided that that divergence isn't too complicated. So let's compute divergence next. Remember how the divergence works? You're just taking the del operator and dotting it with the field. So in general, this is just the del operator dotted with the field M with components M, N, and P. So you take the partial of the first component with respect to X plus the partial of the second component with respect to Y, and then you add the partial of the third component with respect to Z. And in our case, M is X squared. For our field, N is negative 2xy, and P is xy and z squared. So we get 2x, and the partial of this expression with respect to y, that's a constant times y. So we'll just get the constant minus 2x plus the partial of this with respect to z. Xy is a constant, derivative of z squared with respect to z is 2z. So we get 2 times x times y times z, and we're going to integrate that over Q. The question becomes, do you want to go to spherical coordinates? Oops. Or do you want to go to maybe cylindrical coordinates? We've got a region R in the XY plane, that's a circle, a radius 4. I don't think we've done a lot with spherical coordinates, so I think I'll go to spherical coordinates. So the divergence of F was 2 times x times y times z. Actually, I think I'll write that first. And this is Q, and that's dV. And now we'd like to convert this to spherical coordinates. Now in spherical coordinates, theta is that angle that goes around the xy plane. We go all the way around, so theta goes from 0 to 2 pi. Phi is an angle that sweeps. It starts at the positive z-axis, that's phi equals 0, and then it goes down to the xy plane. So phi goes from 0 to pi over 2. And rho, that's the radius of our sphere. Rho equals 0 is at the origin. Rho equals 1 is a sphere of radius 1. Since we go out from 0, 0, 0 to a sphere of radius 4, rho goes from 0 to 4. Now if you're saying to yourself, well, that's not a sphere of radius 4 because we don't have the bottom half, you're absolutely right. Phi takes care of the fact that we don't have the bottom half. Since phi goes from 0 to pi over 2, we get the top half only. Okay, so these are our bounds. So if we're going to convert to spherical coordinates, we need bounds in terms of spherical coordinates. So number 5 is just substitute into the formula. Formula for divergence theorem. And we're here. We need bounds in spherical coordinates, and we just found them. They all happen to be constant bounds. So theta goes from, or let's do rho first. Rho goes from 0 to 4. Phi goes from 0 to pi over 2, and theta goes from 0 to 2 pi. We need an integrand in spherical coordinates. So we need to substitute x in spherical coordinates, y in spherical coordinates, and z in spherical coordinates. Well, in spherical coordinates, x is rho sine of phi times cosine of theta, and y is rho sine of phi times sine of theta, and z is rho times cosine of phi. And then dv in spherical coordinates is rho squared sine of phi. D rho, these are bounds for rho, and then these were bounds for phi, so we'll say d phi, and then the last one is d theta. So we've got our integrand in spherical coordinates. And then we've got dv in spherical coordinates. Okay. So this is it. It's set up. If we actually want the flux through that surface, we need to evaluate this. This is our last example, so I'm just going to evaluate this integral and then we'll be done. At least with the divergence theorem, we'll be done. So I've got the integral from 0 to 2 pi, of the integral from 0 to pi over 2, of the integral from 0 to 4, and let's look at it. We've got 2, we could factor that out. Rho times rho times rho times rho squared is rho to the 5th. And then I've got a sine of phi times a sine of phi times a sine of phi. So there's, I'm just going to start checking things off just to remind myself that I've taken care of it. Sine times sine times sine. So I've got sine cubed of phi, and there's a cosine of phi. So taking care of those. Okay, what's left? I took care of the 2. And it looks like I still have a cosine of theta and a sine of theta. Oh, actually, I think I'm going to bring that 2 over here. Cosine of theta and sine of theta. And there's a trig identity. It's a double angle formula. That's actually sine of 2 theta. This makes the integral a little, just a hair easier to evaluate. Okay. So I'm going to integrate with respect to rho first. So we can factor out anything that does not depend on rho. Actually, I don't need this anymore. I've got sine of 2 theta. That doesn't depend on rho, that's constant. And then I've got sine cubed phi times cosine of phi. And then the antiderivative of rho to the 5th with respect to rho is 1/6. Well, first we add 1 to the exponent and then divide by the new exponent. And we evaluate from rho equals 0 to rho equals 4. So we've got 1/6 here and then a 4 to the 6th minus 0. So that's gone. Okay. And we could simplify that. I'm not going to simplify it yet, but I will. So now we're looking at this integral. We want to integrate with respect to phi next. So that is actually 4 to the 5th times 2 times 2, all divided by 2 times 3. The 2's reduce. And you still have the integral from 0 to 2 pi. And then the sine of 2 theta is constant with respect to phi. So I'll factor that out. And then we're integrating from 0 to pi over 2, this sine cubed phi times cosine of phi d phi. And that d theta is still out here somewhere. Okay, so I see a u substitution. I wrote that this way just to make the u substitution a little bit more obvious. Excuse me. So I'll let u equal sine of phi. Du is cosine of phi d phi. That works out. So we've got u cubed du. And we just need new bounds. When phi equals pi over 2, u is sine of pi over 2, which is 1. And when phi equals 0, u is sine of 0, which is 0. This is very nice, very easy. At 4 to the 5th times 2 over 3 times the integral from 0 to 2 pi of sine of 2 theta. And since this doesn't depend on theta at all, I could just factor that out. This is just going to be a constant with respect to theta. Let's evaluate that integral separately. Now this integral in the red brackets can be rewritten this way. Our new bounds are bounds for u. U goes from 0 to 1. And then this is a u cubed. And this piece is du. So we just evaluate this little integral. And we'll evaluate this little one in a minute. Anti-differentiate. Add 1 to the exponent, divide by the new exponent, substitute in 1 and 0, and subtract. So we just end up with a 1/4. So that 1/4 is going to reduce with one of those 4's. And we just have a 1 there. So we've got 4 to the 4th times 2 over 3 times the integral from 0 to 2 pi of sine of 2 theta. with respect to theta. And then we just anti-differentiate. The antiderivative of sine is negative cosine. And we evaluate from theta equals 0 to theta equals 2 pi. Oh, and I forgot, since there is a constant multiplying that theta inside, we've got to have a 1/2 outside. So I'll take that negative and I'll factor it out. The 2's will reduce. And then we end up with cosine of 4 pi minus cosine of 0. Oops, I guess that's 1 minus 1. So we get 0. It's a little anticlimactic, but it really wasn't too bad. What does that mean? Well, that just means that this flux through the surface is 0. So if F is the velocity field of some fluid, the same amount of fluid that went in is the amount of fluid that came out. So there is no net fluid moving through that surface. And we could verify that if we wanted to by doing the surface integral over S1 and the surface integral over S2. They should be the same number, but with opposite signs, so that when you add them together, we get 0. So maybe whatever goes through S1 goes out of S2, or what goes in through S2 goes out of S1. But it looks like there's no net gain or loss in that flux through the surface. So let's briefly review the theorem. If we have a solid region Q and it's bounded by a closed surface S and it has an outward oriented unit normal, and our field has continuous, has component functions that have continuous first partial derivatives in Q, then instead of evaluating the surface integral, which gives us the flux through that surface, which is the volume of fluid moving through the surface per unit time if F represents the velocity of some fluid, instead of doing that, we can calculate the triple integral over Q of divergence. So what divergence is it's really giving us flux per unit volume. Flux going into this piece, which would be counted as negative, is flux going out of that piece. So that would be counted as positive. What goes out of this one goes into the next one. So we end up with all of these like flux terms that would just cancel as we look at little tiny surface integrals over little tiny cubes. The only ones that will really count, that will actually affect the outcome, are those on the boundary. So now we have this new way of representing divergence, or thinking about divergence. Divergence is flux per unit volume. Now in practice, the way we do this is we sketch our region. We sketch Q and S. We state the theorem. Well, we check the conditions of the theorem, then we state the theorem. Then we just find the divergence of the field. And then we find a way to describe Q. You can use rectangular coordinates, cylindrical coordinates, spherical coordinates, whichever coordinate system is most appropriate. Since we had half a sphere or a hemisphere, we use spherical coordinates. Then we write everything in spherical coordinates, and then we evaluate the triple integral. There was a lot to do, but the integration itself was pretty easy. We just had power rules, a little U substitution. This one would have been a U sub if I hadn't used the trig identity. With the trig identity, we had that KX modification of the sine rule. And it turned out that the flux was 0. So that's the divergence theorem.